In this video, we're going to look at Graham's law of effusion and the similar law of diffusion. So effusion was studied by Thomas Graham, a Scottish physical chemist working in the middle of the 1800s. So Graham studied the rates at which gases would escape from small holes in a container. And so if this represents the container and the small hole, molecules are moving in all directions at all speeds. At any moment, some molecule going in the right direction might escape from the small hole. In measuring this, Graham found that the rate of escape was proportional to 1 over the square root of the molar mass. Okay? So the rate of escape from the hole is inversely proportional to the square root. So 1 over the square root of the molar mass of the gas. Right? So if we express that as an expression, right? Rate is proportional to 1 over the square root of the molar mass. The way we get rid of a proportionality is to add a constant term, right? So we get rate is equal to some constant times 1 over the molar mass. And if we isolate that constant by multiplying both sides by the square root of the molar mass, we get the rate at which the gas is escaping times the square root of the concentration of the molar mass is equal to a constant. And so if we do that for two different conditions, the rate of the first gas times the square root of its molar mass is equal to the rate at which a second gas would escape under the same conditions times the square root of its molar mass. Now, if we rearrange things to isolate rates on one side and the square roots of the molar mass on the other, that is, if we divide both sides by rate 2 and both sides by the square root of molar mass 1, then, right, molar mass 1 becomes 1 on the left side, right? It goes to 1. And rate 2 divided by rate 2 goes to 1 on the right side. And we are left with the ratio of the rates is equal to the inverse ratio of the square roots of the molar masses, right? Rate 1, molar mass 1, rate 2, square root of molar mass 2. And this can be expressed as the square root of the ratio of the molar masses. So this equation is an expression of Graham's law of effusion. Now, again, we can show that this is consistent with the theoretical considerations that we get from the Maxwell-Boltzmann or Boltzmann-Maxwell predictions. Right? Remember that Boltzmann-Maxwell predicted that the square of the mean velocity, right, which eliminates any positive and negative signs, can be predicted as 3 times the gas constant R times the temperature in Kelvin divided by the molar mass in kilograms, right? And so the root mean squared velocity is the square root of that whole quantity. And again, the square root of a fraction is the square root of the numerator divided by the square root of the denominator. So we can separate those two. We can multiply both sides by the square root of the molar mass. So we get the root mean squared velocity times the square root of the molar mass equals the square root of this. If we are at constant temperature, right? So if temperature is constant, then this becomes a constant, and so we can do the same thing we did. If we have the root mean squared velocity of one thing times the square root of its molar mass, that's going to be equal to the root mean squared velocity of another times its molar mass. Again, as long as the temperature and other conditions are constant. And so we can rearrange this to put the root mean squared velocities on the left, the square root of the molar masses on the right, and we get something that looks a lot like Graham's law of effusion. Ratio of rates on the left, inverse ratio of the square root of the molar masses on the right. And so, since the rate of effusion is proportional to the root mean squared velocity, right, we can substitute rate of effusion where root mean squared velocity is, and we still get a ratio of rates, and we get Graham's law of effusion. Similarly, right, rates of diffusion are also proportional to the root mean squared velocity. And so for diffusion, the same equations apply. So the equations that Graham determined for effusion, that is gases leaking out of a container, also apply to gases diffusing and traversing across a distance. Okay, so that's the theoretical basis for Graham's law of effusion, right? It was determined experimentally, but it is also consistent with our theoretical treatment of gases in the Boltzmann-Maxwell equations.